this, as opposed to static electricity, current electricity is moving electricity. So moving charge. Moving charge. So we're going to kind of like roll it back, and we're going to use the Van de Graaff generator as an example. So we looked at one, and we'll just kind of review what goes on with the Van de Graaff generator. And we're going to talk about it in just a slightly different way than how it actually works, but that's okay. So Van de Graaff generator has a metal ball. It's got a base, and we'll just explain exactly what it does. So give me a second while I construct it here. Okay. So it's gonna have to be super tidy here. But inside, it's got a wheel on the top, and it's got a dissimilar wheel on the bottom. Usually one's felt and one's amber. And then there's a latex belt that runs from top. Oh, that's too ugly. I can't handle that. That runs from top to bottom inside of it. And we'll make the latex belt like beige, okay? And the belt just simply spins around. Okay, so it rotates around these guys. So there's a triboelectric effect at the bottom. And like I said, I'm going to talk slightly different than it really works, but that's okay. So what we're going to say is that the latex pulls some electrons off of the amber as it spins by. So what that means is we have sort of a conveyor belt of negative charge being brought up towards this metal ball. Now inside here, you have a metallic comb. Looks like a little brush or piece of screen that's anchored onto the inside of the ball. And then you have here another metallic comb that is actually attached to ground. So this thing gains its charge through triboelectric or friction effects between these two dissimilar rollers and the belt. So as the charge comes up here, keep the charge the same color. Let's keep it like white. Okay. As these negative charges come up into the ball, they pass off into here. Okay. And fill the ball. Okay, so as this runs, the ball fills with more and more negative charge. In reality, these actually fill with positive charge, but that's okay. And you have coming down the other side some positive charge here. Okay, and then when the positive charge gets near here, from the ground, we have more electrons passing into the system as they are attracted up from the ground and into here. So you have this conveyor belt system that continually fills this up with charge. Okay. Now you can imagine that as you add more and more electrons, this becomes more and more negatively charged. Okay, so we'll put a big negative on here on the ball, and we'll draw the field. Okay, and so the field, of course, aims in. We always measure the field with a positive test charge. So this begins to build a field around it. Okay, so we're going to talk about this in a couple of ways. The first way is this. So let's imagine we have this filled with charge and we shut it off. Now that charge is trapped on the ball. It'll slowly leak off over time, but let's just say it's perfectly insulated and the charge cannot leak. Now let's take a little pith ball or something like that, and let's put it right here. Okay. And then let's imagine if we want to move it from that point in the field over to this point. What are we going to have to do to make that happen? First of all, we're going to know that this positive charge is attracted towards here. And so therefore, we're going to have to overcome, and if we think about it here, let's just write something down. We know that that force is going to be equal to Q, which is the amount of charge on here, times E, the strength of the electric field. Remember that from last time, right? This is measured in newtons per coulomb. This is measured in coulombs. And so we get a force in terms of newtons, right? And in order to move against that attractive force, we're going to have to push this thing over, right? So we're going to have to apply some force over a distance. This is a little bit complicated because as we move away, that force will diminish. But the point is this. If I'm applying a force for a distance to move something, I'm working on it, right? It requires work to move between here and here. And what that also means is, if I were to release this, it would of its own accord tend to attract back to where it was, okay? So what we can then say is we've actually given it potential energy by moving it from here to here. So we've increased the potential by moving it over here. Does that make sense? So this is a way that we can talk about different potentials between two different points in space. Okay? We could arbitrarily say this is 0 for potential. If I go this way, I could say that that is positive potential. And if I go this way, I could say that this is negative potential. Okay? Now, you can see that this is arbitrarily defined, and it's a relative thing. Relative to this, this has, sorry, relative, here we'll say A, B, and C. Okay? Now let's call this, a potential of +1 and a potential of -1. We could say that C has a potential equal to +2 relative to A, or we could say that A has a potential of -2 as viewed from B, right? Or we could say that A has a potential of -1 from B, and so on, okay? So potential is between 2 points within a field. Does that make sense? So we have to, when we talk about potential, so we sometimes lose the fact that what it means is it's between different places in a field, and we need to define these values relative to one another, okay? Or we could just as easily say this is 0 and we can only have positive values, right? And then we would say, well, relative to this, this is still negative, B is still -1 from C no matter how we define anything else, right? Sorry, this should be from C. Just fix that quickly. Okay, so this is the concept again, just to remind you. We need to work against this attractive force to push something up here. And kind of like loading a spring, if I've done that, then it's going to spring back there on its own, right? Now, it's kind of a mistake to think about electricity in this way, but I think it's a good illustration of what's going on. In reality, we have to give this a path back, right? So what we could do, right, is we could put something in between here, like say a light bulb or something like that, and we could force that electricity to travel back through the light bulb, and whatever energy I gave it as I worked, whatever potential I gave it when it was here, will drain off as it moves back down to here, right? So if I can't move it directly, if I provide a path for it on its way back down, it will radiate out an equal amount, right, conservation of energy, to whatever work I did, right? So it's got to radiate out its potential. So whatever energy I put in is stored. As it moves back, it radiates out, okay? This also brings into play the concept of what is called equipotential lines, okay? So all that means is, imagine I draw a sphere at the radius that A is on. What that means is anywhere on this sphere, the potential difference is 0, right? So A requires no energy to move from A to A, okay? The potential at B, anywhere along that line, is equal in potential to anywhere else. But going from A to B requires work, and going from B to A liberates energy. Does that make sense? So these lines are called equipotential lines. And okay, that's kind of interesting, all right? So this is one idea. Now, let's just go back to the original setup when we were jamming charge up into this thing. If you've ever messed around with one of these things, you'll hear the motor start to work harder and harder, right? And you'll think to yourself, well, wait a minute, I'm like providing potential energy here, and how that's happening is the motor provides a force up this pulley, or up this belt, right? And the more charge I have here, the harder the motor has to work to push it up there, because there's a resistance to pushing electrons up through this field that we've created, right? They quote unquote don't want to go up there because they're repelled by the electrons that are already there. So work is required to jam them in there. A mental analogy to this that I like to think of is, imagine one of those Joe cans, okay, like a Pringles can, and inside you've got a spring snake. You know what a spring snake is? Okay, so now we've got like these little toy spring stakes, and they're all like jam packed in here. And the more we jam in, the more push or impetus there is for these things to pop their top off and push out of here. Okay, so much like that, we're jamming more and more electrons, just like filling a can with spring snakes, and eventually you'll get so many that they will leap off out through the air and zap something nearby, either your finger or the cabinet or whatever. And they'll ground themselves out, and you'll hear the pitch of the motor immediately drop as this field decreases in strength. And it's easier for the motor to push more charge up, and then it builds up again, pops off, and so on. And you have this kind of like static charge, and then for a second you have movement. Okay? So let's think about what we could do with something like that. Let's think about it. So here we have our big negatively charged ball. We've got all this charge jammed in there, right? So, kind of like what we were thinking about with this, right? You could actually allow electrons to flow out of here. If you give them a path through a conductive wire, they will tend to flow because they are repulsed from here, right? And they will travel down the wire towards the ground, and this is where we can take advantage of them, right? We can make them travel through a light bulb and make light, just like we said before. Maybe we can make them travel through like a toaster, okay, and make heat. I mean, this would make heat and light, okay? We can make them travel through like an electric motor and make spinning, right? You know, like make it into a fan or something, right, that spins around. And eventually, they travel down into the ground and are earthed out, okay? So what we can do is we can measure. Well, let's say in forcing them up into here, okay, and forcing these electrons up into here, we had to do 1 joule of work for every 1 coulomb of charge we put up there, okay? So let's imagine that like this little symbol right here represents an entire coulomb of electrons, okay? If we take 1 joule of work to put that up into there, we could then say that every coulomb, so every C of charge, every C of electrons can do 1 joule of work as it moves to the ground. Okay, so we'll assume, actually, you know what we can do? Let's just take the end off of here and make it ground out right to the machine so we can see how a circuit might work. So we'll ground it out to here. Okay, so let's say that it's getting electrons from the body of the machine and putting them up here. What it's doing is it's raising the potential of them, 1 joule per coulomb, and then as they flow down, they have to leak off 1 joule, okay, per coulomb spread across whatever we hook up here before they reach the ground, and then they're back to 0. So what we would say is this is a 1 joule per coulomb potential on top of this thing. Well, this concept of 1 joule per coulomb, okay, this unit is called the volt. It's 1 volt, right? So electric potential, call it, actually the symbol is V. I shouldn't call it EE. So volts are measured in energy per amount of charge. Okay, so this is a new thing. Energy per amount of charge. We can say this is measured in joules, and this is measured in coulombs. So what we're doing is we're trying to make the leap from the concept of static electric potential to current electric potential. As long as I keep this motor running, right, and as long as it always takes 1 joule to move 1 coulomb up into here, I have a 1 volt circuit, right, that's going to continue to give me, you know, power, right, essentially, okay? This would be a really terrible and inefficient way of generating current electricity, but the theory is there, the concept's there, right? This motor just continually does the work to put charge up here, and that charge naturally, by the repulsion or passage, if you want, through the electric field, pushes down into the ground, okay? So let's try think of a real life example. So in real life, one way to get a direct current circuit like this, and it's direct current because the electrons will always only flow one way, is with a battery. So if you get if you get a AAA battery, AA, I don't think there's an A battery, I'm not sure, a C or a D battery, all of these are 1.5 volt batteries. Okay, so 1.5 volts. And so if we imagine that we have a battery here, okay, it's got a positive end on it, and it's 1.5 volts. Well, what that simply means is the difference in potential between the top and the bottom, between the two ends, is 1.5 joules per coulomb. Okay, how many coulombs of charge are stored in here, right? The capacity of the battery depends on the size of it. Bigger batteries can provide 1.5 volts via a current for longer, for a given amount of current. So let's just see if we can figure out what this is going to do. So we're going to introduce a little symbol here. This is the symbol for a resistor, okay? There's lots of different ways to draw resistors. The old way was kind of like a zigzag. I think more modern ways to just draw like a little block and then write the value of the resistor in here. Now, when I say a resistor, all I mean is something that is radiating the energy out of these coulombs. So this is how I want you to think of it. Each one of these little balls represents a coulomb of charge, okay? Now I'm going to do something to you that you're not going to like. You are going to have to consider these to be balls of positive charge, or little amounts of positive charge, okay? This is the way that classical electricity does it, and I know it's uncomfortable, and I know you're going to tell me, but it's electrons that move. That's true, but all engineering and most physics works on the kind of old school idea that it's positive charges that move. You have to be okay with that, okay? It does not change the math. It's just, just deal with it, okay? So what happens here is each one of these carries 1.5 joules with it, right? 1.5 joules with it. So like a train, right? Each one of these is a coulomb, and each one carries 1.5 joules. When they come back home, they have 0 joules. So when they left, they had 1.5 joules. Then as they traveled through the resistor, they radiated that out. So if it's just a simple resistor, they just simply turn that into heat energy, right? If it's like a heating element, that might be one thing they could do. Maybe they could like run a mix master, or they could run a toaster, whatever, okay? Just the general term for these things is resistors, okay? More specifically, when you get into all the symbols for electric circuits, you'll see symbols for things like electric motors, induction motors, and so on. They do have their own symbols, but for now, we'll just draw this, and this is something that's dissipating the energy, okay? Energy dissipation. Okay, so now there's a few things we have to consider, right? In terms of how much energy overall is coming out of this thing, right? We've got to think about first how much potential there was to begin with, okay? So if we had one battery, well, that potential would just be 1.5 volts. However, we could stack batteries up, and actually, if you put them in this orientation, which is called in series, you actually double the voltage, right? It's additive, right? So you could have the same system with a higher potential, okay? And then depending on the resistor, that would change some other things, okay? So that's one thing to consider. How much energy each one of these packets or coulombs is carrying. The second is how fast that current's moving, right? It could be moving really fast or really slow, and that would change the amount of energy that came out of this. So the first concept that you need to understand is V voltage, how much energy we get for every amount of charge for every coulomb. The second thing we need to talk about is how fast are coulombs moving by. So if we look at this, if we watch and we count, and we have a stopwatch and we time it, current is measured in terms of how many coulombs of charge move by per second. Just like, okay, so current here, right? So let's just label a couple of things. So this, of course, is potential. Its units are joules per coulomb, and that unit is called the volt. all right? Energy here is measured in joules. That's how much energy each coulomb has. It's like how much work was done to move it up here. This is done chemically, but the principle applies. Okay, and this is for each amount of charge in terms of coulomb. Now over here, this is joules. I'm sorry, that's not correct. This is in terms of coulombs per second, and that unit is called the ampere or amp. Okay, joules per second is the amp. This is charge in coulombs, and this is time. So it's how many coulombs per second zip by here. Now we can think of the resistor in this circuit kind of like a throttle if you want. And the way I kind of like, or one way to imagine this is, okay, so imagine this is like a garden hose, right? There's some pressure behind here. And you can think of how it might be like pressure, right? If I jam more electrons in here, it'd be like a pressurized tank of air or whatever. Or like a full balloon. I'm sure you've played with the balloon and you've widened and narrowed the spout of the balloon to allow the air to run out of it. Okay, so with this thing, you can imagine you've got this set amount of pressure pushing out of here, and then you put a resistor in the way. Well, this is like, you know, a rubber bag if you want in terms of like if this is a water analogy, and you're squeezing on it. If you squeeze really hard, you'll slow down the flow of water. If you release, you'll allow more water to go for a given amount of pressure, okay, or push. So the concept of a resistor is kind of like a narrowing of a pipe. So let's say we have a pipe and we have, you know, a liquid flowing through here, and then we have a place where the pipe is narrowed. Well, that's going to serve to slow down the motion through the pipe completely, right? So if I squeeze this tighter, my current, the number of coulombs I'm getting per second, or the number of liters of water, if I'm talking about water per second, is going to decrease, but it's going to decrease in the whole system, right? It's not like you can speed up again after. It's all connected. It's all one thing, right? So you can kind of think about resistance in this way. For a given amount of voltage, how much current do I get, right? If I get a lot of current, I must have a low resistance. If I only get a little bit of current for a given voltage, I must have a high resistance. Does that intuitively make sense to you? Okay, we'll lay down resistors in just a second. Okay, so we're going to leave resistance just for a minute. I just want you to intuitively understand it. Now I want to look at kind of back to fields here. So we're going to explain this kind of idea again, just slightly differently. We'll talk about it in terms of parallel plate systems and fields. So let's imagine that we take a battery like we had before. Okay, and let's use some proper symbols here actually. So the symbol for a cell in a battery is just a wide and then a narrow. And a battery, like a battery of guns, is many cells like lined up. And this comes from the chemistry of how you actually make batteries. When you take electrochemistry in chemistry class, you'll kind of get why it's multiple ones like lined up one after another. So this would be 3 half-volt cells lined up in series to get 1.5 volts. Okay, the big one is the positive and the little one's the negative. So what that means then is this plate, and this represents a conductive plate, a metal plate. We end up with a charge separation, and therefore we end up with a field inside of here. Okay, and so we remember that fields point from positive to negative, always measured based on a positive test charge. So we end up with a uniform field inside of here. Okay, all pointing in the one direction. Now, going back to what we were thinking about before, if we have some amount of charge and we sit it inside the field, okay, and let's say this happens to be positive, okay, if I want to move it from there to there, I'm going to have to do some work. Now, the nice thing about a field that looks like this is the uniformity of the field. So E is uniform in here now. Okay, so unlike where you're radiating out into 2D and that field's getting weaker, inside here, no matter where I place the test charge, the force it feels will be the same, whether it's placed here, 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 or here. It's not to say the potential is the same, but the force on it is the same. So this allows us to like directly calculate how much work we would need to do in moving from one to the next. Okay, so let's think about this. Let's just give this a nice number and say this is a 1 meter separation here, right? And we know that work is equal to force times distance. Okay, But we also know that force is equal to Q times the electric field times D. So the amount of work is equal to QED, right? Now we have 1.5 volts. You've been told this. This is how many joules we have for every coulomb, right? Joules we have for every coulomb. So what that also means then is, in order to move from here to here, work should also be able to be defined then as how much charge we have times how much voltage we have, right? How much charge I have to. So if I have one coulomb, I'm gonna have to do 1.5 joules of work to move it up here. If I have 2 coulombs, it's going to be 3 joules to move it up here, right? So what we've sort of said here is we have 2 ways to define work in a parallel system, right? So we can make these two things equal to each other. So Q times V, the amount of charge times the voltage, right, measured in joules per coulomb, that's the unit that we use, must be equal to Q, the amount of charge, times the electric field, because that gives us the force, times however far we had to move it. Well, Q becomes something that crosses off both sides, and we actually get another way to define voltage. Voltage is equal to field strength times D. Or let's rearrange this to say that, which might be more useful, that the field strength could be figured out from what your voltage is divided by your separation. This is another way to define field strength, okay? So field strength is also known as the volt per meter, or V per M, okay? Because this is measured in volts, this is measured in meters. So should we break it down and just make sure that's true? So if we have a volt, we said a volt was a joule per coulomb, right? So this unit here is joules per coulomb per meter, right? And we said electric field strength should be in terms of what? Newtons per meter, right? Newtons per meter. No, it's not. Yes, thank you. Newtons per coulomb. Okay. So is this and this the same thing? Well, what's a joule? A joule is, right, it's a Newton meter times a coulomb times a negative meter, and there you go, okay? So they are indeed equal units, okay? So that's kind of an interesting thing that you might find useful at some point in time. Electric field strength can also be measured in volts per meter, okay? So it's a little quick derivation and explanation for that. Kind of fun and potentially useful, at least in problem solving. I don't know where you'd use it in real life, but there's probably a place.